Welcome back to Code Meets World. Today we're going to be continuing in the heap priority queue section. Last time we did kth largest element in a stream. This time we're going to look at the last stone weight problem. And the last problem with priority queues was pretty fun and interesting, so hopefully this one is pretty cool as well. So what are we doing here? We're going to be given an array of integers, which are stones, where each integer represents the weight of that stone, okay? So we're going to play a game with the stones, where on each turn, we choose the heaviest two stones, and we smash them together, okay? And these stones have weight x and y, where x is less than or equal to y, okay. So if the stones are the same, I think that means they have the same weight. They're both destroyed. If they have different weights, then X, which is the smaller stone, is destroyed. And the stone of weight Y, which is the bigger stone, now has weight Y minus X. Okay? At the end of the game, there is at most one stone left. So there could be none left. Return the weight of the last remaining stone. If there are no stones left, we just return 0. Okay, great. So we get a thorough example here. Let's jump down to the whiteboard and walk through this. Right. So let me keep the instructions visible because it's a game with steps. So we start out with stones, and those stones are given here. So we have 2, 7, 4, 1, 8, and 1. And I'm just going to work through this example so we can see how this problem would work. So the first thing we do, on each turn, we choose the heaviest two stones, where x is the smaller one and y is the bigger one because of this. Or if they're the same, it doesn't matter which goes for which. Right. So in the first turn, the two biggest stones are 7 and 8. And because those are different, y is the bigger one. So we'll set y equal to 8 and x equal to 7. Great. So now we smash them together. And because they are different weights, the stone of weight x is destroyed. So that means the 7 is destroyed. And we're left with a stone that has a new weight, y minus x. So if we do y minus x, we get 1. So this all results in a stone of weight 1. So I guess technically the 8 stone is destroyed as well. So we smash them together, we destroy the 7 and 8 stone, and we're left with a stone of size 1. So I'll add that back up here to our available stones. So I think that's turn 1. Let's do the same thing for turn 2. So our biggest stone is 4, so that can be y. The second biggest is 2, so that can be x. And then we smash them together, and they will both be destroyed, and we'll be left with a stone of size 4 minus 2, which is 2. So we can add that stone in at the top. Let's keep going because we still have more than one stone in our list of stones. So the biggest is 2, so we can add that here. The next biggest is 1, so we can choose any of them. We'll choose this one. 2 and 1. Those will both get destroyed when we smash them, and we'll be left with a stone of size 1. So we'll add that stone up here. Again, we choose 2 more stones. They're all the same now, so we'll just pick these 2. Now in this case, the stones are equal in weight, so both stones are destroyed. So in this case, they just completely cancel out. We destroy both of these, and now there is at most 1 stone left. So since there is exactly 1 stone left here, we return 1, which is the weight of that stone. And if we go over to our example down here, the output here should be 1. So I think we've gotten that one correct. Yeah, perfect. We do have a second example, which just shows if the length of the stones is just 1 to begin with, we just return that one. So I think that makes sense too. Okay, great. So now let's talk about how exactly we can represent this. Because remember, we're in the priority queues and heaps section. So there should be some way that we can use that data structure to solve this problem. If you remember from my last video, we had to keep track of the smallest value. Well, it was actually the nth largest value, but we were able to store the data in a heap. So we were always keeping track of the smallest value. In this case, I think we want to use a heap to keep track of the largest values at all times. Because if we think about it, and again, watch my last video for a more thorough explanation of what the heap data structure allows us to do. But basically, if we think about our problem again from the start, where we have 2, 7, 4, 1, 8, 1. What we want to do here, I think, is rearrange these values into a heap. But instead of the smallest values being at the top, which is called a min heap, which we used last time, I think this time we want a max heap, where the largest values in the heap are at the top, at the root of the tree. So in this case, we would want our heap to look something like 8, 7, could do 4, could go with 2, and then we would add our 1s, something like this. Because if we store our data like this, on each turn of the game, instead of iterating through this list to find the 2 largest values, which would be pretty slow, I think that would take about n runtime, we can instead, if our data is sorted this way, we know the largest value is at the top, so it's O of 1 to pop off the 8. And then once we pop off the 8, we just pick the largest of these next 2 values to swap up to the root. And then it's O of 1 again to pick the 7. That's a lot faster. So by sorting our values as we go using a heap, I think it will give us a lot of runtime benefits when we're actually solving the problem. So one important thing to point out, I think, is that in Python, when you're using heap PQ, I think is the name of the internal library that I used in the last video, I think it only allows for min heaps, which doesn't work for us here because we want to keep track of the max value. But there's a trick that we can use that I learned when I studied this in school, which was we can choose, when we need a max heap, but only are able to create min heaps, we can just make the numbers negative when we enter them into the heap, and then make them positive again when we take them out of the heap. So what I'm saying is, say we want to store these values, but we only have a min heap. Let's just insert them negatively. If we do that, -8 will be at the top, -7 here, -4, -2, and then we have our -1s, something like that. And then when we remove values, so like when we want to take a value out, we just multiply it, whatever it is, by -1, which will give us, in this case, 8. And that way, we can use a min heap to store max values, if that makes sense. I think it'll make more sense when we go ahead and look at the code here in a second. So let's go ahead and try to write this and see if we can get it to work. Okay, So now that we've talked about how we can design this solution, let's go ahead and write it and see if it works. So I think what we want to do first is create a priority queue. And then we're going to heapify that priority queue. So remember in the last video, I did the same thing. We just create an empty array, and then we can call this heapify command, which is internal to the Python library, and it will turn that list into a priority queue. Now this is a min heap. So remember, we need to do this trick that I just talked about where we insert values negatively, but we'll get to that in a second. So now let's add all of our values. So for stone in stones, what we can do is the heap push function, which takes as arguments the heap that we are pushing to, and then the value we want to push. And now here's where we have to make it negative, because it's a min heap, but we want to store max values. So we're going to make it negative each time that we insert. Great. So once we've done that and the priority queue is filled with all of our values, the next step is to just start looping, because we want to play the game until there are 0 or 1 stones remaining. So we can say that while the length of the priority queue is greater than 1, we want to keep playing. And remember how we play. We first have to assign y to be the largest value and x to be the second largest value. So we've made this extremely easy for ourselves, because we now have a priority queue where the top value is the largest value. So we can simply say heap pop. I think I need an extra p there. Heap pop. And we say the priority queue that we're popping from. And now, because we're using this trick where we invert all the values, we need to make this negative as well. Because up here, we inserted, for example, -8. So now when we take that value out, we want to take the -8 and change it back to a +8. So that's why I've inverted that value. Now, once we pop the largest value off, what we know about the heap data structure is it automatically will update itself and make the switch so the next highest value moves into the highest spot, the root of the tree. So as soon as we pop the biggest value, the tree alters itself, so the largest remaining value is now at the top again. So what that means is, to get x, which is the second largest value, we can say heap pop again. And again, we need to invert it. So now these values, y and x, have the largest and second largest values in the entire priority queue, in the whole heap. Once we have both of these, remember our game instructions. If x equals y, both stones are destroyed. So in the case where these are equal, I don't need to do anything else, because by removing them from the heap, they're just gone, meaning they're destroyed. The only case I have to check is if they're not equal to each other, because then I have to create a new stone and add it into the priority queue. So if x does not equal y, then what we can say is we need to create a new stone that is the difference between the two stones. So we could say heap push onto the priority queue, and the value we want to push is y minus x, the biggest minus the smallest. And again, we cannot forget that we have to make that value negative to align with the little trick we're doing to make it into a max heap. So again, in this case, if they're the same, we don't need to do anything because they just get destroyed. If they're different, we need to push onto the priority queue a new stone that's the difference between the two. So once we've done all this, which plays all the rounds of the game, we just need to check if the priority queue is empty or if it has one stone left. So if the length of PQ is 1, we want to return whatever that value is. So we can say PQ 0, which takes whatever that value is and returns it. Otherwise, we simply return, I think the problem said, 0, like that. Great, so let's go ahead and run this and see if it works. Okay, so it's not working. Let's see why. Oh, okay, yeah. I forgot my trick at the end. So we need to also make this value negative, because anytime we put something in or take something out, we have to invert it. So let me see if that fixes it. Perfect. Let's go ahead and submit that. Incredible. So there we go. That's a pretty good solution. And as another quick recap, we simply make an empty list, turn it into a heap or a priority queue. Then we loop through all the stones and push them on to the heap. Then we play the game until there are 0 or 1 stones left. And finally, we check to see if there's 1 stone left or 0 and return the value that we need to return. So thanks so much for watching, and I will see you in the next video.